This is Honors Algebra 2 Pre-Calculus. We're doing section 9.5 in Pre-Calc, which is the Binomial Theorem. All right, so let's first start by talking about what we're talking about when we talk about the Binomial Theorem. So if I asked you to do a plus b to the 0, right, assuming that a and b are non-zero, right, like a plus b does not sum to 0, a number to the 0 power is 1, right? If I asked you to do a plus b, the whole binomial, right, it's a binomial with two terms to the first power, you would tell me that it was just a plus b, right? You wouldn't do anything to it. If I asked you to do a plus b to the second power, you would write that as a plus b times a plus b, and you do that thing we call foiling, right, which is really just extended distribution, and you'd get an a squared. Your outer and inner would both be an a times b, so you'd get plus 2ab, and then you'd get a plus b squared, right? If I asked you to do a plus b to the third, you'd have to write a plus b times a plus b times another a plus b. You would FOIL these two to get this first expression, right, that we just got here for a plus b quantity squared, and then you'd times this expression by a plus b again with more extended distribution, and you would end up getting an a cubed plus a 3a squared b plus a 3b squared a plus a b cubed. All right? And again, there's a reason I know that, and you're not expected to know that off the top of your head, but what I want you to start to notice is immediately this gets way more complicated as we keep going down, right? If I asked you to do an a plus b to the fourth, right, that would mean an a plus b times another a plus b times another a plus b times another a plus b. And there's a couple different ways that you do this. One option is that you'd FOIL these two together, and you'd FOIL these two together to get 2 of this, and then you do extended distribution to figure out what you get, right? But I think what you're getting is that this is not this is sort of an untenable option. Like, you're not just going to keep foiling forever, right? You could definitely figure this out if you had to, right? It's going to end up being a 4a cubed b plus a 6 a squared b squared plus a 4ab cubed plus a b to the fourth. Okay, there you go. So, but I'm not going to go any further with this because it's awful. All right, so the binomial theorem essentially gives us a way to do this a lot faster. Now, we're going to talk about a couple of different ways to do this. One of them is the binomial theorem, and one of them is we're going to walk through a little thing called Pascal's triangle. So I'm actually going to do this in the opposite order of the way that your book does it. Instead, I'm going to walk you through Pascal's triangle first. Now, your book has Pascal's triangle. So your book has this basic setup. I think they used X's and Y's, but they have this basic setup on page 654, okay? What I'm going to do is, before we go ahead and talk about the stuff they're going to talk about, we're going to jump ahead for a sec and go to page 656 and talk about Pascal's triangle. So Blaise Pascal, because he's got a tough first name, he made this triangle. So Pascal's triangle. And Pascal did a bunch of other stuff, but for our purposes, we mostly care about his triangle. So this is what Pascal's triangle looks like. Pascal's triangle starts with a 1 at the top. Okay, and below that 1, the next tier is a 1 and then another 1. And the way his triangle is going to work is the outside values are always going to be 1s, okay? So there's a 1 on the outside. Now, the next tier, you're going to put a 1 on the outside, but to get the number in the middle, you're going to sum the two numbers above it. So 1 plus 1 gives you 2. The next tier is going to start with a 1 and end with a 1, but to get the numbers in the middle, you're going to sum the numbers above them. So you're going to get 1, 3, 3, 1. The next tier of the triangle is going to start with a 1, end with a 1, but the numbers in the middle are going to end up being a 4 because you sum the 1 and the 3, a 6 because you sum the 3 and the 3, and a 4 again. So you get 1, 4, 6, 4, 1. So what I want you to show you about that is I want to compare this triangle that I have down at the bottom, to the coefficients that I got up here. Notice that when I had a plus b to the 0, I just got a 1. Well, this is row 0 of Pascal's triangle, which I know feels weird because you want to call it row 1, but it's row 0. The reason it's row 0 is because this is the coefficients if you have a plus b raised to the 0 power, right? A plus b to the 0 power, I just got a 1. The next row is called row 1 of Pascal's triangle, and you'll notice that its coefficients correspond to a plus b to the first. There was a 1 in front of the a, and there was a 1 in front of the b. The next row, the row that has the 2 in it, right? So the row that has the 2 as the second term, sure enough, those coefficients correspond to the coefficients of a plus b quantity squared. Notice that I have a 1, 2, 1, and that's exactly what's in this row, 1, 2, 1. The next row, which would be row 3 of Pascal's triangle, again, you can't miss that it's row 3 because even though technically you see 4 rows, it's the row that has the 3 in it. Well, sure enough, those are the coefficients I get if I do a plus b to the third, and you can see that if you look at what I expanded here. 1a cubed, 3a squared b, 3b squared a, 1b cubed. Well, 1, 3, 3, 1. And then sure enough, if I do a plus b to the fourth, I get 1, 4, 6, 4, 1 as my coefficients, right? And I could keep going with Pascal's triangle, right? So notice that 1, 4, 6, 4, 1. I could keep going with Pascal's triangle forever, right? The problem is that it gets really annoying and tedious. And we're going to talk about how I knew what powers go with what things, and I'm going to walk you through an example using Pascal's triangle in a second. After we get through example 1, then we'll go back and we'll revisit exactly what the binomial theorem says. For small powers, like 2, 3, 4, Pascal's triangle is the easier way to do this instead of the binomial theorem. For very large powers, like a plus b to the 20th, it wouldn't make sense to work yourself down to row 20 of Pascal's triangle. That would be a weird choice. So one way to think of Pascal's triangle is essentially this is a recursive formula, right? We learned about this when we talked at the beginning of sequences and series. To find the next row of Pascal's triangle, you use the row above it. Now, I would suggest that you memorize the first couple rows just because it's easier, but if I wanted row 7, I don't know row 7 of Pascal's triangle. If I really needed row 7, I would have to work my way down to row 5, 6, 7, and when I get to row 7, then I'd be good. But because you're using the row above it, it's recursive. That means that finding row 20 or row 57 would be a nightmare unless we have some explicit way to jump to that row. The binomial theorem gives us a way to jump to whatever row of Pascal's triangle we want. I could jump to the 100th row, I could jump to the 10th row, I could jump to the billionth row. It would not be a good idea, but I could. So essentially, Pascal's triangle is a recursive visual formula. And the binomial theorem is an explicit formula that lets us jump to any row in the triangle. Cool. So let's do an example. So I'm going to walk you through how I was able to figure out what powers go where when we do a problem like this. So in example 1, we're going to fully expand, and we're going to start with a plus b to the 5th. Okay, now I already did a plus b to the 4th for you on that little intro, so we're just going to walk through a plus b to the 5th. So here's how it works. What this tells me is that if I'm going to use Pascal's triangle instead of the binomial theorem, this tells me I need to use row 5 of the triangle for coefficients, okay? So I'm going to make a note. I already know what row 4 was because we just used row 4. So row 4 was a 1, 4, 6, 4, 1, which means row 5 starts with a 1. 1 plus 4 gives me 5, 4 plus 6 gives me 10, 4 plus 6 gives me 10 again, 1 plus 4 gives me 5, and it ends at a 1. So these are my coefficients, okay? So what I'm going to do is I'm going to write out that a plus b to the 5th is 1 blank space plus 5 blank space plus 10 blank space plus 10 blank space plus 5 blank space plus 1 blank space, okay? Because those are the coefficients. But now I have to figure out what the actual variables are. So this front seat, which is an a, is going to start at the highest possible power, which would be a to the 5th. And then it's going to go down 1 each subsequent term. And you can see this by, if you go back in the video and look at what I did at the beginning, you'll see that that's true. Notice there's no a in the very back term because that would be an a to the 0. This back seat, which is a positive b in this case, and it will matter if it has a minus, is going to start at its highest power at the very back, b to the 5th. And then it's going to have its powers descend as I move towards the left, right? So b cubed, b squared, b to the 1st. And when I get to the very first term, I should have no b at all. So that's my fully expanded form. Now, let's go ahead and call that example 1a so I can give you one that's slightly different, right? So let's say, so we'll call that a. Let's say I do the same thing, but I ask you to do something a little bit harder. Let's do x minus y to the 3rd. Okay, so that means that I'm going to use the 3rd row of Pascal's triangle, but what I want you to notice here is that this is actually x plus a negative y, right? That y is going to have a negative sign, which means the different powers are going to matter on that y. So I know I'm going to use the 3rd row of the triangle. If you need to work your way down to it, it's fine. I know it's 1, 3, 3, 1, right? And again, if you don't know that, that's totally okay. I do a lot of math. So I know the coefficients are going to be the 3rd row of Pascal's triangle. So I know this thing's going to equal 1 blank space plus 3 blank space plus 3 blank space plus 1 blank space, right? I'm then going to take the front term, which is the x, and I'm going to start it at the highest power, which would be cubed, and I'm going to lower the power each time as I go down until I get none of that term at the back of the thing. I'm going to do the same thing with my negative y, but I need you to notice that it's a negative y. So negative y to the third, negative y to the second, negative y to the first, and then no y at all. Well, why that matters is that those signs are going to become an issue. So I'm going to get that this is an x cubed. Because this negative y to the first, it's a first power. That means it's an odd power, and that negative y is going to say negative. So I'm going to get minus a 3x squared y, but then this negative y is squared, so that's going to come out positive. So plus 3xy squared, and then this y cubed is going to come out with a negative because it's an odd power, and this is going to be my final answer.